Hello everybody, this is Joseph with the DLASC, and today we're going to be talking about ranking compounds based on acidity. So, the first compound we're going to look at and then we have, and finally, it's supposed to be a benzene ring. I'm sorry, it's kind of ugly. Never been good at drawing those. Okay, so what we're going to do is we're going to rank these three compounds in order of increasing acidity. So, 1 is going to be the most basic, 3 is going to be the strongest acid. So when you're ranking acidity, the first thing you want to do is draw the conjugate base of whatever compound you're dealing with. So if you're familiar with the definitions of conjugate bases and conjugate acids, the conjugate base of these three acids are going to contain, it's going to be the same, we're just taking away a proton. So this is going to look like this. And remember, you got to keep track of your electrons and your charges. Okay, so these are our three conjugate bases. So we're going to be using our conjugate bases to determine the acidity of the original compound. So there's something to remember about the strength of a base. It's inversely related to the stability of the base. So the more stable the base is, the weaker it is as a base, making the acid stronger. Because remember, strong acids have weak conjugate bases, and vice versa. Strong bases have weak conjugate acids. So if we have a strong base here between these three conjugate bases, that means our conjugate acid is going to be weaker. So to determine the stability, let's look at some resonance structures. So this one, we can resonate these electrons on this O, the O with the negative charge, can form the double bond with that carbon, and it'll kick the electrons onto the other O. So that'll look like this. And I believe those are the only two resonance structures we have for that one. Next we have this one. I don't think there are any other resonance structures for that. So now we can move on to this one. So these electrons can form a double bond. Let me make sure that doesn't look like it's touching the carbon. It should form a double bond. And that will kick this double bond onto this carbon. So we're given this. This carbon now has a negative charge. This O is now double bonded. Now these electrons can form a double bond here, kicking this pi bond onto this carbon. Remember this O. Now once again, these electrons can form a double bond here, and this double bond will form a negative charge on that carbon. And then finally, needs to form a double bond here, kicking these electrons back onto the oxygen. Hold on, I just made a grave mistake. Carbon never has 5 bonds. Let's get rid of that. Remember I said it kicks these electrons onto this oxygen. So these are all the possible resonance structures for our the conjugate base of our third compound. So now we're going to determine stability, thus determining strength of your base, thus determining strength of your conjugate acid. So we're going to be looking at, so resonance structures are important to look at. So it would be easy to conclude that our third compound is more acidic, because the resonance structures that we have here are higher in number than the first compound. And generally, more resonance structures equals more stable base. And then remember, it's inversely related to the strength of the base. So the more stable the base, the weaker the base, the stronger the acid. But there's another key detail to pay attention to here, outside of the number of resonance structures, and that's to look at charges on specific atoms. So if we look at the third compound's conjugate bases, resonance structures, we can see that on most of these resonance structures, there are these electrons on carbons. Now you should know that carbons are not very electronegative. They do not like to hold negative charges or electrons. Inversely, oxygen, if we go back to the resonance structures of our first compound's conjugate base here, oxygens are extremely electronegative. They love to hold all the negative charges and electrons, in relation to carbon at least. So in 60% of the resonance structures on the right, the negative charge is on a carbon. In both of the resonance structures on the left, the negative charge is on an oxygen. So that tells you the ones on the left, that conjugate base is more stable than the conjugate base on the right, because the electrons are distributed between two electronegative atoms like oxygen, as opposed to these on carbon. So that lets us know it's a very stable base. So this one is the most stable base. Now, since this one doesn't have any resonance, this one is the least stable base. And this one's in the middle. So what does that mean? That means a stable base, the more stable it is, that means the weaker it is. The less stable it is, the stronger it is. Okay, so if we know which one is our most stable base, our least stable base, we know which one is our weakest base and our strongest base. That means we know which one's our strongest acid and our weakest acid. Because remember, if it's a weak base, a weak conjugate base is probably going to be it's going to be a strong acid. So since this one is our weakest base, it's going to be our strongest acid. Conversely, since this one is the strongest base, it's going to be our weakest acid. If it's the strongest, it's the weakest, this one falls in the middle. So if we're ranking these based on acidity from low to high, our weakest acid would be this one. That would be number 1. This one falls in the middle. This one would be number 2. And this one would be the most acidic, the strongest acid. And just to verify, I can give you the pKa values of all of these. This one is 4.8. Remember, the lower the pKa, the more acidic. This one's 16. And this one's 10. So there's a quick crash course on how to rank a few few compounds based on acidity. I hope you found this helpful, and I will see you in the next one.